Hello friends, in the previous lecture we discussed about the basics of memory devices. We learnt about the units of memory, the read and write operation of data from the memory, addresses of data and its locations, and finally the classification of RAM into SRAMs and DRAMs. In today's lecture we shall be talking about the SRAM and DRAM organization. Asynchronous SRAM organization. An asynchronous SRAM is one in which the operation is not synchronized with a system clock. To illustrate the general organization of a SRAM, a 32K into 8-bit memory is used. A logic symbol for this memory is shown in this figure. In the read mode, the 8 data bits that are stored in a selected address appear on the data output lines. In the write mode, the 8 data bits that are applied to the data input lines are stored at a selected address. The data input and data output lines share the same lines. During read, they act as output lines, and during write, they act as input lines. Tri-state buffers in a memory allow the data lines to act as either input or output lines and connect the memory to the data bus in a computer. These buffers have 3 output states: high, low and high Z, that is open. Tri-state outputs are indicated on logic symbols by a small inverted triangle and are used for compatibility with bus structures such as those found in microprocessor based systems. Physically, a bus is a set of conductive paths that serve to interconnect 2 or more functional components of a system or several diverse systems. Electrically, a bus is a collection of specified voltage levels and or current levels and signals that allow the various devices connected to the bus to communicate and work properly together. For example, a microprocessor is connected to memories and input output devices by certain bus structures. An address bus allows the microprocessor to address the memories, and the data bus provides for transfer of data between the microprocessor, the memories and the input output devices such as monitors, printers, keyboards and modems. The control bus allows the microprocessor to control data transfers and timing for the various components. Memory array. SRAM chips can be organized in single bits, nibbles, bytes or multiple bytes. Figure shows the organization of a typical 32K into 8 SRAM. The memory cell array is arranged in 256 rows and 128 columns, each with 8 bits. There are actually 2 to the power 15 addresses, and each address contains 8 bits. The capacity of this example memory is 32,768 bytes, or typically expressed as 32 kilobytes. The working of SRAM is explained through this block diagram. First, the chip select must be low for the memory to operate. 8 of the 15 address lines are decoded by the row decoder to select one of the 256 rows. 7 of the 15 address lines are decoded by the column decoder to select one of the 28 8-bit columns. In the read mode, the write enable input is high and the output enable is low. The input tri-state buffers are disabled by gate G1 and the column output tri-state buffers are enabled by gate G2. Therefore, the 8 data bits from the selected address are routed through the column input output to the data lines, which are acting as data output lines. In the write mode, write enable is low and output enable is high. The input buffers are enabled by G1 and the output buffers are disabled by G2. Therefore, the 8 input data bits on the data lines are routed through the input data control and the column input output to the selected address and stored. Read and write cycles. Figure shows typical timing diagrams for a memory read cycle and write cycle. For the read cycle, a valid address code is applied to the address lines for a specified time interval called the read cycle time. Next, the chip select and the output enable inputs go low. One time interval after the output enable input goes low, a valid data byte from the selected address appears on the data lines. This time interval is called the output enable access time. Two other access times for the read cycle are the address access time, measured from the beginning of a valid address to the appearance of a valid data on the data lines, and the chip enable access time, measured from the high to low transition of chip select to the appearance of valid data on the data lines. During each read cycle, one unit of data, a byte in this case, is read from the memory. For the write cycle shown in figure B, a valid address code is applied to the address lines for a specified time interval called the write cycle time. Next, the chip select and the write enable inputs go low. The required time interval from the beginning of a valid address until the write enable input goes low is called the address setup time. The time that the write enable input must be low is the write pulse width. The time that the input write enable must remain low after valid data are applied to the data inputs is designated TWD. The time that the valid input data must remain on the data lines after the write enable input goes high is the data hold time. During each write cycle, one unit of data is written into the memory. Basic synchronous SRAM with burst feature. Unlike the asynchronous SRAM, a synchronous SRAM is synchronized with the system clock. For example, in a computer system, the synchronous SRAM operates with the same clock signal that operates the microprocessor, so that the microprocessor and memory are synchronized for faster operation. The fundamental concept of the synchronous feature of a SRAM can be shown with this figure, which is a simplified block diagram of a 32K into 8 memory for purposes of illustration. The synchronous SRAM is similar to the asynchronous SRAM in terms of the memory array, address decoder and read write and enable inputs. The basic difference is that the synchronous SRAM uses clocked registers to synchronize all inputs with the system clock. The address, the read write input, the chip enable and the input data are all latched into their respective registers on an active clock pulse edge. Once this information is latched, the memory operation is in sync with the clock. For the purpose of simplification, A notation for multiple parallel lines or bus lines is used in figure as an alternative to drawing each line separately. A set of parallel lines can be indicated by a single heavy line with a slash and the number of separate lines in the set. The address bit A0 through A14 are latched into the address register on the positive edge of a clock pulse. On the same clock pulse, the state of the write enable line and chip select are latched into the write register and enable register respectively. These are 1-bit registers or simply flip-flops. Also, on the same clock pulse, the input data are latched into the data input register for a write operation, and data in a selected memory address are latched into the data output register for a read operation, as determined by the data input output control based on the input from the write register, enable register and the output enable. Two basic types of synchronous RAM are the flow through and the pipelined. The flow through synchronous SRAM does not have a data output register, so the output data flows asynchronously to the data input output lines through the output buffers. The pipelined synchronous SRAM has a data output register as shown, so the output data are synchronously placed on the data input output lines. The burst feature. As shown in figure, synchronous SRAMs normally have an address burst feature which allows the memory to read or write at up to 4 locations using a single address. When an external address is latched in the address register, the two lowest order address bits A0 and A1 are applied to the burst logic. This produces a sequence of 4 internal addresses by adding 00, 01, 10 and 11 to the two lowest order address bits on successive clock pulses. The sequence always begins with the base address, which is the external address held in the address register. The address burst logic in a typical synchronous SRAM consists of a binary counter and exclusive OR gates as shown. For a 2-bit burst logic, the internal burst address sequence is formed by the base address bits A2 to A14 plus the two lowest order bits of internal burst address. To begin the burst sequence, the counter is in its 00 state and the two lowest order address bits are applied to the inputs of the XOR gates. Assuming that A0 and A1 are both 0, the internal address sequence in terms of its lowest order bits is 00, 01, 10 and 11. Cache memory. One of the major applications of SRAM is in cache memories in computers. Cache memory is a relatively small high speed memory that stores the most recently used instructions or data from the larger but slower main memory. Cache memory can also use dynamic RAM. Typically, SRAM is several times faster than DRAM. Overall, a cache memory gets stored information to the microprocessor much faster than if only high capacity DRAM is used. Cache memory is basically a cost effective method of improving system performance without having to resort to the expense of making all of the memory faster. The concept of cache memory is based on the idea that computer programs tend to get instructions or data from one area of main memory before moving to another area. Basically, the cache controller guesses which area of the slow dynamic memory the CPU will need next and moves it to the cache memory so that it is ready when needed. If the cache controller guesses right, the data are immediately available to the microprocessor. If the cache controller guesses wrong, the CPU must go to the main memory and wait much longer for the correct instructions or data. Fortunately, the cache controller is right most of the time. Basic DRAM organization. The major applications of DRAMs is in the main memory of computers. The difference between DRAMs and SRAMs is the type of memory cell. As you have seen, the DRAM memory cell consists of one transistor and a capacitor and is much simpler than the SRAM cell. This allows much greater densities in DRAMs and results in greater bit capacities for a given chip area, although much slower access time. Again, because charge stored in a capacitor will leak off, the DRAM cell requires a frequent refresh operation to preserve the stored data bit. This requirement results in more complex circuitry than in SRAM. Several features common to most DRAMs are now discussed using a generic 1M into 1 bit DRAM as an example. DRAMs use a technique called address multiplexing to reduce the number of address lines. Figure shows the block diagram of a 1M bit DRAM with a 1M into 1 organization. We will focus on the blue blocks to illustrate address multiplexing. The green blocks represent the refresh logic. The 10 address lines are time multiplexed at the beginning of a memory cycle by the row address select and the column address select into two separate 10-bit address fields. First, the 10-bit row address is latched into the row address latch. Next, the 10-bit column address is latched into the column address latch. The row address and the column address are decoded to select one of the 2 to the power 20 addresses in the memory array. The basic timing diagram for the address multiplexing operation is shown in this figure. Read and write cycles. At the beginning of each read or write memory cycle, row address select and column address select go active, that is low to multiplex the row and column addresses into the latches and decoders. For a read cycle, the read write bar input is high. For a write cycle, the read write bar input is low. Fast page mode. In the normal read or write cycle described previously, the row address for a particular memory location is first loaded by an active low row address select, and then the column address for the location is loaded by an active low column address select. The next location is selected by another row address select, followed by a column address select, and so on. A page is a section of memory available at a single row address and consists of all the columns in a row. Fast page mode allows fast successive read or write operations at each column address in a selected row. A row address is first loaded by a row address select going low and remaining low, while column address select is toggled between high and low. A single row address is selected and remains selected while row address select is active. Each successive column address select selects another column in the selected row. So, after a fast page mode cycle, all of the addresses in the selected row have been read from or written into depending on the read write bar. So, friends, that brings us to the end of our discussion in this lecture, and therefore, we sum up. In this lecture, we learnt about the memory organization of SRAMs and DRAMs, asynchronous and synchronous memories with burst feature. A cache memory is a small fast memory between the CPU and main memory. The refresh operation prevents data from being lost because of capacitive discharge. A stored bit is restored periodically by recharging the capacitor to its nominal level. And finally, we learnt that DRAMs use a technique called address multiplexing to reduce the number of address lines. So, that is it for today. See you in the next lecture with more on memory. Thank you very much.